Hello, discrete math fans. So we can list a lot of relations that involve unions, intersections, complements, and differences. Some of these are going to be true no matter what sets you put in there. Others will fail depending on what sets you put in. So in this section, what we're going to do is show how to establish some basic set properties, and we're going to use element arguments. We'll even talk about a variation that's used to show that a set is empty. The book has arguments like that. We may not go over any here, but you can look those up in the book. So let's list a few basic subset relations. So the first one is inclusion of intersections. So for any sets A and B, A intersect B is always a subset of A, and A intersect B is always a subset of B. Then we have inclusion in union. So for any sets A and B, A is a subset of A union B, and B is a subset of A union B. Finally, we have a very important property. This is the transitive property of subsets. For all sets A, B, and C, if A is a subset of B and B is a subset of C, then it must be the case that A is a subset of C. Now these properties that we just went over, they're true of all sets, and we'll prove some of them. Now in order to prove these, what we're going to need is something that we'll call a procedural version of set definitions. So that procedural version looks like this. We let x and y be subsets of some universal set U, and then we'll suppose that little x and little y are elements of U. And so we have various things like little x is an element of big X union big Y if and only if little x is an element of big X or little x is an element of big Y. So there's a lot of them like that, so I won't go over all of these. These follow basically right from the definition of what union, intersection, difference, and complement, and in this last case, Cartesian product. Okay, that's all for now.